everyone, thank you so much for coming to my talk. So essentially, like, I want to share with you the thing that we have been working on, both in my research group, but also at Together as a company that we kind of founded last year. So like, essentially, everyone here just witnessed this amazing progress of machine learning and AI, right? So if you look back last year, we got so many models. We got stable diffusion, right? So I mean, almost every single week, there's some crazy model out there. So if you look back in the last decade, right, so all of those are progress that we can actually measure in a more quantitative way, right? If you look at the ImageNet score in the last like 20 years, if you look at, for example, squat, NLP benchmark, I mean, you can see in the last like 5 years to a decade, so there's almost this like a 20 to 30% improvement of the quality of the model. And because of that, right, so we start to see machine learning get into every single corner of our life. Of course, there are so many things that actually come together to actually make all those advancements happen. But I would argue fundamentally there's these two different driving forces that has been keep pushing us forward. And they are the data and also the compute. So there are different ways for us to look at this. But one example is this paper from OpenAI a couple of years ago. You can see on the left-hand side, right? So the more data you push into the system, right, the better, at least in this application, the better the model that's going to become. But of course, all those data are not free, right? The more data you push into the system, the more compute that you are going to burn, and the more compute you are going to burn, the better the model is going to become. And because of a phenomenon that looks like this, it's actually not surprising if you look back history in the last 30 years, think about how does the data set kind of evolve. We actually go a very long way. We start all the way from the biggest data set that we have as a community's ImageNet, 1.3 million images, all the way to today, people are pushing like billions of images into the training process. But of course, right, so the more data you push in, the more compute you are going to burn. And if you want to do, for example, GPT-3 style model, right, we are talking about a couple thousand GPU running nonstop for a month, right? So that doesn't even give you the most expensive model that you can train today. So we have been like going a really long way on both data and also on the compute. But there are also challenges that we are facing today. So the fundamental challenge I think we are facing today as a community is that even though we know how to build those machine learning applications, actually building them can be ridiculously expensive, and both on the data and also on the compute side. So just put some number onto it, right? So the first bottleneck is about communication and data movement, right? Because training anything at scale is super expensive on the communication side. So for example, if you want to do like 6 billion model, right, training for 300 billion tokens, right? If you have 32 machines, 4 GPU each. So essentially, we are talking about during the whole training process, every single machine going to send and receive 4 petabytes of data to each other. Even if you have a very fast network, like 100 gigabits network in the data center, we are talking about this is a workload that requires you to do 100-hour communication, and when the computation itself is only 200 hours. So it's really expensive on the communication side. And if you want to do an even larger model, it becomes even more expensive on the communication side. And if you look into this, right, so that is the reason that today model training are largely restricted to centralized data centers with very fast network connections. It's very hard for you to use cheaper alternatives like tier 2 to tier 4 clouds, spot instance, volunteer compute, simply because how expensive the communication is. And if you look into the future, right, so I would argue if you want to scale this by another 10 times, even inside data center, it becomes kind of challenging because you start to build essentially the same fast connection over 10 times more machines. So the second bottleneck in building those models comes from essential data quality, right? Because the more data you push into the system, almost inevitably, right, so the data quality starts to decrease. And this is just one example, right? If you query doctor in line of 5B, this is essentially what you get. And we can see there's a whole bunch of data quality issues, right? First one, I mean, there are some data noise, right? So this 2 picture doesn't really give you doctors, right? That's a big problem. And second, even more seriously, I would argue there's a very serious gender bias in what is inside this data, right? So, and all those problems, in your data set, are being reflected in today's open model. If you have noise in your data, your model might be low quality. If you have bias in your data, your model might have fairness and bias issue. And these are actually hurting us today as someone who is building an open model, And if you look into the future, if you want to scale your data set by another 10 times, I would argue as a community, we are in a dire need to really develop the high-quality core of your data to actually feed our model and try to understand data quality in a more principled way. So essentially, at Together and also in our research group, we try to look at this essentially two bottlenecks. And the way that we think about space is by thinking about it as a tension between three different players. So on one hand, you have your data set, right? So that is actually the problem, essentially causing more problems. So data become larger, right? Become more complex. The quality of data start to decrease, and the amount of effort you need to put into clean the data, acquire new data, start to increase. And as a consequence of that, your models start to get bigger, get more complex, and both the data and the model is actually adding pressure to the infrastructure side. You start to use a whole bunch of floating point operations and storage to actually train the model, to serve the model. And as a consequence of that, so the infrastructure start to evolve in two different ways. It start to specialize, and on the other hand, it start to scale out. So when everything gets right, when you actually start to break the tension and have the kind of the information flow between these three different players, amazing things happen, right? One of the example is this llama moment, right? If you think about what happened here, right, there's a huge data set being actually pushed into the training process, and on the other hand, it's also burn a whole bunch of compute. But once you get your data and compute right, you get this amazing model. So in our research, the thing that we are curious about is essentially how can we break the tension between these three different players and enable interesting things. So we essentially look at the infrastructure and also look at the data set. So today I'm going to share with you some of the things we have been working on essentially on both fronts. So let's talk about infrastructure. One thing that we are really curious about infrastructure is really try to optimize distributed infrastructure and also decentralized training. So why do we care about that? The reason we care about that is the communication and data movement are essentially the key bottlenecks in scaling up distributed learning. So this is true for centralized infrastructure, right? So a couple of months ago, we trained this Red Pajama model. It's actually trained on one of the most powerful supercomputer in the world. It's actually a very fast connection, and this is actually the scaling curve. So x-axis is how many GPU you are actually using for the training side, and the y-axis is actually how many samples per second you are getting. So as you can see here, right, so the green line is the ideal scaling, and the blue curve is actually what we actually get out of the system. So there's a gap between the green and the blue line. It looks like a very small gap, but this actually means almost 500 GPUs are being idle because of the communication in this very busy supercomputer. So, and this happens for centralized infrastructure, but on the other hand, if you move to another extreme of the spectrum, if you think about all those decentralized network, when every single computer is being connected by 100 megabits network, communication becomes an even larger bottleneck. And of course, there are infrastructure in the middle, for example, multi-cloud spot instance, and also serverless environment. The more you move from the left to the right, communication becomes slower. But if you can actually accommodate your workload to the infrastructure on the right-hand side, potentially we increase the pool of compute, and hopefully that can actually lower the cost for our user. So one thing that we have been doing over the years is essentially try to understand from the algorithm perspective or from the system perspective, how can we accommodate slow network? So this is our workload, right? You have a neural network, you have a training set. So once you have this, you can draw a sample from the training set, and then you can do two things. You can do a forward pass to evaluate the loss, and then you can do a backward pass to compute the gradient for every single layer. And of course, sometimes the model is too big, right? So, and you need to do multiple data samples in parallel, forming a mini batch. Then you have these two parallel pipelines. And sometimes the model is really big, doesn't fit in a single machine. You start to cut this neural network into different pieces. So as you can see here, right, so there are essentially three different communication channels in the system. So you need to communicate the forward activations during the forward pass, the backward gradient during the backward pass, and also the data parallel gradient during the data parallel training thing. So one thing that we learned over the years is that essentially all three communication channels can be kind of compressed really aggressively without hurting the model quality too much. So if you're interested in this, right, we can look at one of the channels, for example, the model, like the data parallel channel. So we write a very small book about this, have a whole bunch of things like about what we can do here. So one thing that we are really excited is an algorithm called Coulter SGD in this year's SML. So essentially, this is just a really high-level like idea about how the algorithm works. So essentially, you have a whole bunch of machines. Everyone is holding a model replica, and then they just proceed as if all the other machines doesn't really exist. But of course, they need to communicate. So the way that we think about communication is try to fully overlap communication with computation. Right? We have this like communication slot, and this is the time that all the other workers are actually doing computation. So essentially, we try to come up with a global state delta t. This is the communication, and then we try to accumulate to the local state. The high-level idea is as long as the communication fully overlap with computation, there's no slowdown caused by the communication. But of course, the key is actually how to design this delta t, right? What information should we communicate at every single round? Remember, we are talking about like 100 megabits network. So if you look at this, one high-level idea we are very excited about is you can actually have a mixture of communication compression techniques. So look at the delta t, right? First one, it has a single step stillness, right? But at every single step, right? So we combine three different methods. We randomly sample a subset of parameters to communicate. And then within that subset, we do a top k gradient, and then we quantize the value. And then essentially, you do a low precision communication in the end after you compress this vector in these three different ways. So the high-level idea behind this is essentially we need to compose different compression techniques all together to give you something really, really aggressive. If you want to compress your communication by like 100 times, if you go for a single method, you kind of very easy to go really far in one dimension. You start to hurt your like convergence. You kind of need to combine different methods together into a single framework. So I won't go into detail about the theory, but essentially the whole thing works, right? So this is actually two different models. The first one is a 6 billion model. The second one is a 20 billion model. And this is all about about instruction tuning. So as you can see, right, the green curve is Coulter SGD compressed by 100 times, right? So as you can see, even though we are compressing communication by 100 times, you are getting almost the same convergence as a full precision setting. On the other hand, if you pick a single method like top k on local SGD, right, and if you compress them by 100 times, you start to see this rather big gap in terms of convergence. And this actually makes the system side very interesting, right? So here the x-axis is actually the network bandwidth. The y-axis is how many samples you can process every single second. So as you can see here, even though your network could be like 1 gigabit, 500 megabits, once you compress your communication by 100 times, you are getting almost the same throughput as if you are in a very beefy data center network. So potentially, this could mean that data parallel training over 1 gigabit network is actually possible. And you can do different algorithms for every single channel you see in this graph. And one thing that we have been doing is to have another framework, try to do, for example, 3-bit forward communication, 6-bit backward, and 4-bit data parallel gradient. And we are cutting this model into 8 different pieces, right? Even for an environment look like this, right? We are actually getting almost the same convergence as if you are not compressing at all. But on the other hand, when you have this like geo-distributed 8 cities and you're cutting this model 8 different pieces, right? When you have a network like 500 megabits between different of the workers, you are getting essentially like almost the same throughput as if you are in the data center setting. So we are actually very excited about this because potentially this means that if you can actually make your decentralized compute, for example, 1.5 times cheaper, it starts to make economic sense, right? That's why we are kind of very excited about that. So, and this is just one thing we are doing on the infrastructure side. So another thing that we are doing is actually on the data side, right? Try to break this tension in another way. So on the data side, one thing that we have been working on is a project called Red Pajama. And the high-level idea is really to have this open data recipe and also this recipe for data quality to build large language models. The goal is really try to get llama quality and also beyond. So why do we want open data? The way we think about open data and open model is by thinking about them as these 4 pillars of openness, right? So in the bottom, right, it would be great if you can have open weights, right? So you have your model that we can use, great. But that's not really the full picture of being open. The second pillar is about open license, right? Everyone can use that for commercial purpose. But more importantly, we would argue that the data being open is also important. Because once you know what actually get into this model, you can refine your data, you can filter your data, you can process your data. You can start to align the data into the application that you actually want. And you have this kind of insurance that you know what actually get into the model. And also what's even more important than having this open data is to have an open data recipe to make sure if you have another application, you can actually apply the same processing step, have the same recipe to actually help more people to build their applications. And today, if you look at open models, not all of them actually cover the 4 different pillars. And the goal of the projects is really try to build something for the community to criticize and for the community to actually build on. So the first version of RedPajama starts from kind of a well-defined goal. We kind of take the Llama 1 model and read the paper and try to reproduce the data as a starting point. So it contains 1.2 trillion tokens. There's like 7 slides of data, right? So we try to match the token count of the Llama 1 paper as close as possible. And in the end, there's a 1.2 trillion tokens in the whole data set. And then we try to do as close a quality filter as possible compared with the paper. So one thing that we are really excited about is to see how people are using and also refining, right? So like this Red Pajama data set, there's actually a whole bunch of open models actually use some of the slices in Red Pajama that we are actually very happy about. And our own effort, right? So it start to train models of like 1 trillion tokens. We kind of start from the PCA architecture, right, to make sure we can actually tease apart the influence of the model architecture and also the influence of the data set. And on the other hand, we do instruction tuning. There's a separate data set there. We have a tuning for chat model. There's another data set that we are building together with Lion called OIG for the chat model. And then we are also have a data set for moderation, right? So when you actually mount your chatbot, right, there are actually 2 models running there. One is try to make sure we do proper moderation, and the second model is actually answering the question. So we have data for actually all of them, for the base data, for instructions, for chat, and also more importantly, the moderation model. So, and the model active factor is actually very interesting. So there's a 3 billion model that kind of surprisingly getting a lot of attention, right? So I think one reason behind it is kind of very small, right? If you actually quantize the whole thing into 4-bit, it's kind of like 1.5 gigabyte. It's fit into a cell phone, right? So together with Tianqi, I mean, he had this very interesting demo on iPhone, right? You can actually chat with the model actually locally, right? If you go to App Store, you click install, you actually have this model, because it's very small, shipped together with the app. And it's actually not a bad model, right? If you look at the quality like on Helm for the average score, once you properly instruction tune it, you can actually use the model to do a whole bunch of things as the other larger model, for example, 7 billion model. But of course, it kind of instruction tune. But on the other hand, if you actually want to do tasks that fit into the instruction tuning, it's actually a useful model. And the 7 billion model trained on Red Pajama data set, right? So it's kind of, there are multiple things that we learn. So first one is we make monotonic progress over the last generation of open models, especially GPT-J and NeoX, and also PCA, right? So we start to make monotonic progress in the sense of benchmark score. Another thing is open models are still lagging behind, right? On Helm, you see this 3 to 4 points gap between essentially Red Pajama and essentially other open models and also with Llama, right? So there's like 3 to 4 points gap that we kind of need to fix from the open model side. And also with instruction tuning, the model can become kind of more powerful. It's very promising, but still a very long way to go. So another thing about open data is once you open the data set, you can do very principled, transparent contamination analysis to make sure when you evaluate on some benchmark, you can actually prove to everyone we are actually not trained on that benchmark, right? The quality you are seeing coming from the model is really the quality of the model, right? So we actually do very rigorous and very kind of aggressive contamination and decontamination of the instruction site, right? So essentially, there's no overlapping at all between the instruction tuning phase and any of the benchmark data set that we run. So this is kind of one of the things that actually coming out of the open data because you actually know what actually get into the model. So, but there's still a lot of work to do, right? So evaluation is a very big problem, right? You all see like kind of this story, right? So on the Hugging Face leaderboard, right, the Falcon used to be very high. Falcon is an amazing model, right? So kind of very high, higher than Llama. And after this tweak, right, if you tweak the benchmark a little bit, go back to the original one, you'll start to see their relative order start to change. So we are not here to argue which one is the right one, right? But the fundamental question that we actually do not know how to answer is how should we evaluate and compare those large language models in a more robust way? Maybe human evaluation is a key, but how to scale it? And also, even if you use human, how can we make sure it's reproducible and also unbiased? We have no idea how to do this. So second problem is essential data quality, right? So the way that we think about data quality is you have all those slices in RedPajama, also in other open data set. For every single slice, it has a very different quality compared with other slices. What is the weight? What is the principal way to actually learn about the relative importance between these different data slices? How can we do deduplication, right? So one thing that's really interesting is a company called Cerebras. They're actually really amazing. They actually take RedPajama and just very aggressively just deduplicate it, right? They actually bring it down to like 700 billion tokens, right? They released something called SimPajama. We are really happy that they find our data useful and build on it. How can we think about data transformation? How can we think about data debias, data detoxic, right? There's a whole bunch of work I think the community need to do to really try to understand, first of all, how to define the signal for the quality, and second, given the signal of the quality, how can we actually learn what actually get into our model? So the second version of RedPajama, we start to work on it, right? So the goal is really to try to provide, first one, like a much larger data set compared with RedPajama V1, but on the other hand, give people this principled framework to start to think about and reason about data quality as a whole. So that's actually the goal. So this is actually my last slide, right? So together, we are start to build this framework and platform to do inference, to do fine-tuning for a whole bunch of open models, right? If you go to api.together.xyz, right, you can actually play with this, right? So right now, there's like 50 different open models. You can do inference, you can do fine-tuning, right? So please go there and actually give us feedback. So yeah, thank you so much for your attention, right? So I'm happy to answer every question.
Thank you so much for this amazing talk. Let's get some questions.
Hey, what's with the name, Red Pajama?
Yeah. Yeah, so one thing about Red Pajama projects, we got a really good name. So it's actually come from a kid's book, Llama Llama Red Pajama. Yeah, so essentially, the version 1 tried to essentially reproduce the llama data recipe, right? So we think really hard, probably longer than we should have, about what name that we put in. Yeah, so and at the end of the day, right, there's llama, so there's Red Pajama. Yeah, that's the name.
Any other questions?
When talking about people iterating on Red Pajama, you mentioned slices, some 5 out of 12 slices. Could you give more details on what are slices of Red Pajama?
Yeah, so I think, I mean, there is, so first time we don't know whether it's the right way to group them into these 7 different slices, right? So the slice here, essentially, they come from different sources. There's Common Crawl, there's Wikipedia, right? So here by slice, we mean different source. But fundamentally, the thing we are thinking about in RedPajama v2 is to not have this artificial definition about slice, right? Because there could be Wikipedia-like data in Common Crawl, right? Where does that come from? Common Crawl slice. So we are trying to define kind of slicing in a more parametric way, right, in RedPajama v2, right? But I think for v1, that's essentially where data actually come from. Yeah.
Maybe a last quick question, or otherwise we move to the...
Coming.
Hello. A great talk, thank you. For your work on compression, I noticed that the different communication channels need different number of bits.
Yeah.
Do you have any insight as to why?
Yeah, so it's kind of, so those three different channels, it's kind of, some of them are very difficult to compress, right? So the data parallel channel is kind of the easier one because, well, as long as you have unbiased gradient, you have unbiased kind of convergence in an informal sense, right? So it's kind of easier to compress. The forward activation is very, very hard because if you make the error in layer 1, it starts to propagate, and start to explode, right? So we have a whole bunch of things to do for the error compensation, right? There's a whole bunch of techniques can actually control the explosion, right? But on the other hand, there's some channels simply more difficult than the other ones. Yeah.
Okay, thank you.